Hi everyone, welcome back. In this video we will work a weak acid strong base titration. So let's consider the titration of 20 milliliters of a 0.105 molar acetic acid with 0.125 molar sodium hydroxide. So remember to always kind of think of the design of the titration, what's in your beaker, what's in your burette. And so it says that we're titrating acetic acid, so H C2H3O2. And it's important to recognize, is this a strong or is this a weak acid? It's not one of the strong acids, so it must be weak. In our burette is sodium hydroxide. And what is sodium hydroxide? Excellence, a strong base. So anytime you have a titration problem, always identify what's in your beaker and what's in your burette. It'll change the way you approach the problem. For example, in the previous video, we did a strong acid, strong base titration. And so no rice tables were needed in that particular video, but they will be needed in this video here. All right, so let's get started. The initial pH. And we ask ourselves, what's in my beaker at this point of the titration? Only acetic acid, which is our weak acid. And we've learned before that if we want to find the pH of a weak acid, we need to do a rice table. So you first need to write down the reaction that's taking place, the partial ionization in water, and the conjugate base of acetic acid is acetate. Water has to act as a base, so it's a proton acceptor. So the conjugate acid of water is the hydronium ion. So initially, what do you put into your beaker? 0.105 molar. Remember with rice tables, when we're working with aqueous solutions here, we're always working in molarity. And we'll assume that nothing else was in there at the initial start, that the initial hydronium ion concentration from the autoionization of water is negligible. And at equilibrium, you add up the initial and the change, so 0.105 minus 1x is minus x. 0 plus 1x, x. 0 plus 1x, x. Because you're working with a weak acid equilibria, then we need to use the Ka expression to help us solve for x. Because our goal is to find the pH of the solution. We can find the pH from the hydronium ion concentration at equilibrium. So basically, in this case, we're solving for x. Ka equals products over reactants. Which is x squared over 0.105 minus x. The Ka value is 1.8 times 10 to the negative fifth. For acetic acid, We will assume that X is small enough to ignore because we see that the initial concentration is significantly larger than the Ka value. So in this case here, X is equal to 1.37 times 10 to the negative third. And as we recognize from the Rice table, that's also equal to the hydronium ion concentration at equilibrium. Therefore, pH is equal to the negative log of the hydronium ion concentration which is equal to 2.86. Always ask yourself, does this make sense? I'm given what's in my beaker. What's in our beaker is a weak acid. So yes, we do expect to see an acidic pH less than 7. All right, the next part's asking us to calculate the volume of added base required to reach the equivalence point. Now let's write down what the equivalence point means. So you always hear that the equivalence points is the moles of acid equals the moles of base. And that's true, but I want to be clear what base we're talking about here. So a lot of times you'll hear me say it's the moles of whatever's in your beaker is equal to the moles of what's in your burette. In this case here, we've identified that what's in our beaker is acetic acid. So there's your acid. And what's in our burette is the sodium hydroxide. Because there's another base in solution, right? There's the conjugate base of acetic acid, which is acetate. But when we say moles of acid equal to moles of the base, we're talking about whatever is in our beaker to whatever is in our burette. Okay? So now that we're doing a reaction here, because we're adding base, and we're neutralizing all the acid in our beaker. That's what it means to reach the equivalence point. Then we will need to use a Baugh table. First things first, we have to write down the reaction. So we have the acetic acid reacting with our base. Now sodium hydroxide, side note here, in solution, breaks up into the sodium cation and hydroxide anion. So I'm only going to use the base here, the hydroxide, as part of this equation. I'm only showing you the net ionic equation and just excluding sodium since it's a spectator ion. So I'm adding hydroxide. Hydroxide's a base. It's going to pull off a proton and make the conjugate base of acetic acid, which is acetate. And the conjugate acid of hydroxide is water. All right, it's proton acceptor. It went from OH to H2O. All right, so our Baugh table stands for before addition, addition, and after addition. And you must always, always work in moles because essentially it's a nice table to illustrate the stoichiometry. So rather than doing a bunch of dimensional analysis, since everything is 1 to 1 to 1 to 1 with these acid-base titrations, then the Baugh table is a nice way to identify the limiting reactant really quickly and to also see what's left over after the addition. Because we must work in moles, we need to convert the molarity of the acetic acid in our beaker from the volume that was given. So we were given 20 milliliters of a 0.105 moles acetic acid solution, molar solution. So therefore, That's 0.020 liters. I'm converting 20 milliliters into liters by dividing by 1,000 and multiplying by its concentration. So that liters cancels out. And so in our beaker, always to start before addition is 2.1 times 10 to the negative third moles of acetic acid. So we will use that calculation throughout this problem here. So before addition, I have 2.1 times 10 to the negative third moles of acetic acid that I have in my beaker. I haven't added any hydroxide yet. Haven't produced any of the acetate, and we exclude water. All right, so the purpose of the equivalence point is for the moles of whatever's in my burette to equal to the moles of what's in my beaker, the acetic acid. So I need to add this number of moles so they completely neutralize one another here. So I'm adding 2.1 times 10 to the negative third moles of base, which reacts, and so I'm going to subtract that out because it's reacting with my acetic acid. And so after the addition, I have a 0 amount of moles of acetic acid left over. I have 0 amount of moles of the base left over. But remember, as we're reacting these two together, we're creating this conjugate base. And so I'm creating 2.1 times 10 to the negative third moles of the acetate. So let me just review over that again. So at the equivalence point, the moles of what's in our beaker is equal to the moles of what we add from the burette. So I started with 2.1 times 10 to the negative third moles. I added 2.1 times 10 to the negative third moles of hydroxide, which reacted with my acetic acid. And so since these moles reacted, I'm left with 0 amount of hydroxide and 0 amount of acetic acid in my beaker. But what I do have in my beaker left over is the conjugate base here. And that is the conjugate base of a weak acid, so therefore it is a weak base itself. And so basically you'll have a weak base equilibria. Now part E is asking for the pH, so I'll do that in a little bit. We'll come back to this again. But what this part of the question was asking was what was the volume that was needed to reach the equivalence point. So we know now that we needed to add 2.1 times 10 to the negative third moles of sodium hydroxide, or of the hydroxide. We know the concentration we added was 0.125 moles per liter. And then if we wanted to convert that to liters, milliliters from liters, liters cancels out, moles cancels out. So we need 16.8 milliliters of sodium hydroxide solution to reach the equivalence point of a 0.125 molar sodium hydroxide solution. All right, so part C is asking for us to calculate the pH after 5 mils of the base, sodium hydroxide, is added. All right. So once again, when you add anything to your beaker, so we're adding 5 mils of base, we need to do a BA table. We need to see what happens after that base is reacting with our acetic acid. So let's go ahead and write down the reaction again. We have acetic acid plus the base, the hydroxide. That pulls off a proton, creates the conjugate base of acetic acid, which is acetate, and the conjugate acid of hydroxide is water. Always remember to work in moles, because this is a stoichiometry table essentially. And so we started with 2.1 times 10 to the negative third moles of acetic acid in our beaker. So always go back to the beginning. Before addition, what was in your beaker? And then 0 amount of the hydroxide and conjugate base. All right, so if we've added 5 mils of a 0.125 molar sodium hydroxide solution, then how many moles have we added? Well, we need to use the molarity and the volume. I converted the 5 mils into liters. 1 second. Should be 0.005 liters times 0.125 moles per liter of the sodium hydroxide. And then from there, you get 6.25 times 10 to the negative fourth moles of the sodium hydroxide. So that's what you're adding in. That's the addition. And when you get to this point here, you ask yourself, well, what is my limiting reactant, right? So one where you have the fewer moles, because everything's 1-to-1 here, and that's why you're able to do that trick and not worry about the mole-to-mole ratio like you would in a typical stoichiometry problem. So your limiting reactant here would produce the least amount of product, right? In this case, it's the one with the fewest moles. And so therefore, since hydroxide is our limiting reactant, then it will be completely consumed. So you'll have 0 amount left over because it's reacted with the acetic acid. So we will subtract out that many moles because it's reacting with our acetic acid. And we have 1.475 times 10 to the negative third moles of acetic acid left over. But remember, as we're reacting, we're creating product. We're creating conjugate base. So we want to add that in here on this side of the equation. All right, so always ask this question here. What's in my beaker? What's in your beaker at this point in time after you've added the hydroxide is acetic acid and acetate. Acetic acid, which is a weak acid, and acetate, which is its conjugate base. It's a weak base. If you have a weak acid and a conjugate base, what do you have in your beaker? You have a buffer. All right, we've already determined that X is small enough to ignore for this problem here. And I've taught you before, if you have a buffer and X is small enough to ignore, then what equation can you use here? Excellent. You can use the Henderson-Hasselbalch. Remember, for buffer solutions only. So we will use the Henderson-Hasselbalch equation. I'm first going to convert to concentration just to see what we have left over in concentration and molarity. So whenever you do that, you want to make sure that you add up the total volume that's in your beaker after the addition. And so we initially started with 20 milliliters of acetic acid. We've added 5 milliliters of the sodium hydroxide, so you have 25 milliliters left over, which is equal to 0.0250 liters. Okay. And so therefore you would take the number of moles divided by the total volume. So the concentration of acetic acid, like after you've added base, is equal to 1.475 times 10 to the negative third moles per liter. Which ends up being 0.059 molar. You do the same thing for the conjugate base. So you take 6.25 times 10 to the negative fourth moles divided by the total volume. So always be careful with that. Use the total volume so you get the correct answer. And in this case here, the acetate concentration after the addition of the base is equal to 0.025 molar. So now I'm going to plug that in. Remember, Henderson-Hasselbalch is pH is equal to the pKa plus the log of the conjugate base over the acid. So pKa is negative log of Ka, so I'm going to say negative log of 1.8 times 10 to the negative fifth plus log of the conjugate base. So this is where also I've seen students accidentally flip them. So it's really important you identify, well, what's my conjugate base? So this number should go on top here, and then this number will go on the bottom. So conjugate base over the acid. And when you plug that into your calculator, you should get 4.37 for your pH. You ask yourself, well, does this make sense? I'm given where I'm at in my titration. Well, let's look at the initial pH. So initially, our pH was 2.86. Now we've added 5 milliliters of a strong base. So do you expect your pH to be slightly more basic? Yes. So it's still acidic, right? Because all that base was still neutralized. This is still the limiting reactant. So we still expect an acidic pH, but it's increased due to the fact that we've added a strong base. We have now some of this conjugate base in solution, which increased that pH. Okay, so just to review over here, we added 5 milliliters of a strong base. After our Baugh table, we realized we have both the weak acid and its conjugate base, so this is essentially a buffer in our beaker at this point in the titration. Because X is small enough to ignore, we can use the Henderson-Hasselbalch equation. But to do that, make sure when you convert to your concentrations that you divide by the total volume in your beaker after you've added the 5 milliliters of sodium hydroxide. And then the Henderson-Hasselbalch is pH is equal to the negative log of Ka plus the log of the concentration of the conjugate base over the acid, and you get 4.37. Now, if you feel more comfortable doing a rice table, you could have done a rice table as well. Once again, working only in these concentrations here, you could have done a weak acid equilibria rice table, but remember, these are your initial concentrations that you would plug into that rice table. And that's probably a good practice for you to do anyways, to see if you can get the same answer that we got from the Henderson-Hasselbalch using the rice table as well. All right, so part D was asking us, what is the pH at 1/2 the equivalence point? So let's continue on here. So the pH at 1/2 the equivalence point, this is just a really good trick to remember, so it saves you a lot of time. The pH is equal to the pKa. The reason why that is at 1/2 the equivalence point, the concentration of the weak acid is equal to the concentration of its conjugate base. Basically, you've converted half of that weak acid into the conjugate base by adding the strong base, the sodium hydroxide. So if the weak acid and its conjugate base are equal, if you were to plug that into the Henderson-Hasselbalch, because essentially you still have a buffer at this point in the titration, the log of conjugate base over the acid, well, if they're the same concentration, that would be a log of 1, which is 0. And so that is why the pH at 1/2 the equivalence point is equal to the pKa, because the concentration of the weak acid and its conjugate base are equal. A log of 1 is 0. So that's where we get that derivation from. Okay? So therefore, pH in this case is equal to the negative log of 1.8 times 10 to the negative 5th. That is 4.74. There you go. So we're reaching 1/2 the equivalence point here. Now the next one here is when we want to find the pH at the equivalence point. So we've already figured out like the volume of added base required to reach the equivalence point. And so now the pH at the equivalence point is based on what's left in our beaker, right? So coming back to part B actually here. This was the equivalence point. We realized that we don't have any of the acetic acid and hydroxide left over because they neutralized each other. All we have is the acetate, which is a weak base. So it's important to recognize, like, at the equivalence point, I have a weak base, then I need to do a weak base equilibria. And we need to also work in molarity here. And so the total volume here. So let's go ahead. So what's in my beaker? Is acetate, which is a weak base. That tells me I need to do a rice table, KB. I also need to determine my total volume. I started with 20 milliliters of my acetic acid, and then the volume to reach the equivalence point was 16.8 milliliters. So 36.8 milliliters is my total volume. I use that because what was left over in my beaker was the 2.1 times 10, let me write that down, times 10 to the negative third moles of the acetate. So to figure out the concentration that I will use in my weak base equilibria rice table, I will take the number of moles and divide it by the total volume. Don't forget. So 0.057 molars. That's what's in my beaker initially. So now we're just doing weak base equilibria in the presence of water. The conjugate acid is acetic acid. The conjugate base of water is the hydroxide. Initially we have 0.057 molar of the acetate and 0 amount of the acetic acid in the hydroxide. Acetate changes by minus 1x, plus 1x for the products, and then at equilibrium, initial plus change, minus x. Because this is a weak base equilibria, we will need to use the Kb of acetate. Now we have the Ka, though, of acetic acid. It's conjugate acid. Remember, Kw is equal to Ka times Kb. So if you need to figure out the Kb of your conjugate base, you can take Kw at 25 degrees Celsius over the Ka, which is 5.56 times 10 to the negative 10th. And so Kb is equal to products over reactants so that's x squared over 0.057 minus x is equal to 5.56 times 10 to the negative 10th. X is going to be small enough to ignore because the initial concentration is much greater than the Kb here. So we get x is equal to 5.63 times 10 to the negative 6, which happens to be our hydroxide concentration at equilibrium. From there, we can figure out the pOH is equal to negative log of the hydroxide ion concentration. So pOH is equal to 5.25. And then pH is equal to 14 minus the pOH, which is equal to 8.75. All right, so at this point in the titration, we recognize that what's in our beaker is only a weak base. So you cannot use Henderson-Hasselbalch here. It is not a buffer, only a weak base. But we've done weak base equilibria before, and so you want to use a rice table. You want to take the number of moles that you calculated from the BOD table. So that was in part B, by the way. So you want to take these number of moles and divide it by the total volume here, 36.8 milliliters, to get the initial concentration of acetate. in this weak base equilibria problem. Then we had to solve for Kb from the Ka, use the Kb expression because we're working with the weak base, find X, which was our hydroxide ion concentration, and from there the pH. All right, still onwards. What is the pH part F after 5 mils of base is added beyond the equivalence point? All right, so part F. 5 mils, so let's just write that down so we remember. pH after 5 mils of sodium hydroxide is added beyond the equivalence point. So therefore the volume of the sodium hydroxide is equal to 16.8, which is the amount we needed to reach the equivalence point, plus 5 milliliters is equal to 21.8 milliliters of sodium hydroxide solution that we're adding. Once again, we're adding it to our beaker. We need to do a Ba table. So we write down the reaction that's taking place when we're adding our base. We're always working in moles here. Initially, before addition, we had 2.1 times 10 to the negative third moles of acetic acid, 0 amount of the hydroxide, 0 amount of the acetate. Now we need to figure out the concentration of the base that is added, or the number of moles of the base that is added here. And so it's a 0.125 molar solution. We have 0.0218 liters that we're adding. And then it's 0.125 moles of sodium hydroxide per liter. So liters cancels out. So we're adding from our burette 0.02725 moles. Or 2.725 times 10 to the negative third moles. That's the addition here. And remember, at this point, you always ask yourself, which one is my limiting reactant? In this case, everything's 1 to 1 to 1. So it works out to just compare the moles. Like, that's not always what you do for stoichiometry problems, but in the Ba table we can because we're only transferring 1 proton. And it looks like my acetic acid's my limiting reactant because I have fewer moles. So it will be completely consumed. So we will lose those 2.1 times 10 to the negative 3 moles and have none of the acetic acid left over when we're beyond the equivalence point. Now, most of this base was reacted with the acetic acid, so we need to subtract that amount from what we put into our beaker. So what's left over in excess is 6.25 times 10 to the negative 4th moles. And like I said, this is excess. Now, when you learned in first semester general chemistry to calculate the excess reactant, now you see where it comes into play in this application here. All right, so as we're reacting acetic acid with the hydroxide, we're creating the conjugate base. So we have acetate also in our beaker. All right. So let's write that down. What's in my beaker? You have a strong base, and you also have acetate, which is a weak base. So we have hydroxide, which is a strong base, and you have the acetate, which is a weak base, what do you think is going to dominate the pH of the solution? Definitely the strong base. We've seen that before. We've discussed about a mixture of acids, and if you have a strong acid and a weak acid, the strong acid dominates and suppresses the equilibrium of the weak acid. So the same thing goes for a mixture of bases. If we have a strong base and a weak base, then the strong base helps to suppress the equilibrium of the weak base. So we don't have to worry about doing a race table here. We just calculate the pH based on the strong base only. But first things first is we need to figure out our concentration. And so we need to figure out what our total volume is. So we have volume total is equal to the 20 milliliters of acetic acid that we had originally, plus we added 21.8 milliliters of the sodium hydroxide. So we have 41.8 milliliters of the total volume, which is equal to 0.0418 liters. And so when we look at the hydroxide concentration, we take the number of moles in excess that are unreacted after we've added it to our beaker, and we divide that by the volume. And we get 0.01495 molar. And the pOH is equal to the negative log of the hydroxide ion concentration which is equal to 1.825, and the pH, remember, is equal to 14 minus the pOH. And that is equal to 12.18. All right, so you ask yourself, once again, based on what's in my beaker, does the pH make sense? Now, what's left in our beaker is just a bunch of base, right? It's definitely a strong base, some of the weak base, and so having a pH of 12.18 does make sense here. It is a basic solution at this point in the titration. All right, so the final thing that we must do here is to, plot the titration curve. So we need to take all these data points. So the initial pH of being 2.86, so that's before anything was added. At the equivalence point, we add 16.8 milliliters of sodium hydroxide. After 5 milliliters of base, we have a pH of 4.37. At half the equivalence point, which is about 8.5 milliliters, we have 4.74 pH. The equivalence point at 16.8 milliliters is 8.75. And then 5 milliliters beyond the equivalence point of sodium hydroxide added, we have a pH of 12.18. So we want to sketch that. All those data points here. remember when you're doing a titration curve, you want pH on the y-axis and then the volume of whatever's in your burette. So this will be volume of sodium hydroxide added in milliliters. All right, I'm going to do increments of 2 here, 4, 6, 8, 10, 12, 14. I'm going to do 5, 10, 15, 20, and there we go. I think 25. All right. So we found that the pH was a little bit above 2 when 0 amount of the sodium hydroxide was added. I'll have to go back again and find after 5 milliliters was added. We found the pH to be 4.37. At about half the equivalence point, we found it to be about 4.74. At the equivalence point, it was, let's double check that again, at the equivalence 8.75. And by the way, a lot of times students want to say 7. The pH is 7 at the equivalence point, but that is only for a strong acid, strong base titration. It's not true for a weak acid, strong base titration, nor is it true for a weak base, strong acid titration. Always ask yourself, what's in my beaker? It's a weak base. So yeah, for this titration, we do expect the pH at the equivalence point to be basic. Okay, so 8.75. It's about 16.8 milliliters of the base added. And then after 21.8 milliliters of sodium hydroxide is added, our pH was 12.18. So remember that these titration curves look like kind of like a letter S. Here, let me show you. So it'll look like this for like a weak acid, strong base titration. If you're doing like a weak base, strong acid titration, then it will be the reverse, where it would have started a high pH and then go to a low pH. So it's just kind of the reverse of this one here. But here we start acidic solution, and as we add more base, we reach the equivalence point. And this was half the equivalence point, by the way, half the equivalence point. And then once we reach the equivalence point, we've neutralized all of our acids. So then if you add any more base, the pH is going to shoot up right there, right? It's going to go super high. And yeah, so therefore, just once again, you start off with acidic pH, half the equivalence point, pH is equal to the pKa, and then you keep adding more base. You reach the equivalence point where the moles of acetic acid are equal to the moles of sodium hydroxide. Just want to write this down again, just so you can remember. This is the moles of the acetic acid were equal to the moles of the hydroxide here. So they were completely neutralized. Nothing was left over except for our acetate. And then after that, we're just adding a bunch of base. And so that's why the pH shoots up to about 12. All right. So that was a long problem, but hopefully working it through step by step was clear to you. If it's not, please let me know if you have any questions. I highly suggest that you try to do this problem again on your own without looking at the answer. Ask yourself, every step of the way, like, how do I get the products of this reaction? Do I use a Baugh table? Do I use a Rice table? Do I use Henderson-Hasselbalch? Do I work in moles or do I work in concentration? So make sure you're very mindful of all the details here, so that if you're given a titration problem, you can identify the steps and apply what you've just learned in this video. All right. Thank you all for watching, and I will see you next time.